So let's get started. Just to make some announcement, which I also make in the Blackboard. Next Monday, we don't have class because that one will be rescheduled to the end of semester, where we'll cover our programming, optional tutorial at the end. Because of some of you told me that they just not only learn Python but also learn R, and that would be at the end of we do it at the end of semester. Sometime we book the B.A. lab because the main problem is using the our program. You cannot use your iPad, so we have to use computer. So we book some computer lab, and we'll make it like the Python. Python, you still can use the iPad, that's fine. But the R will be easier to do the lab thing. I mean, it's optional anyway, so there's no change in the syllabus or what, but just optional thing. Just try to cater for your some of you want to learn more, but it's not in the exam or not in the homework. So in case you worry about that, there's no extra thing to be worried about. Okay, it's not asked in the exam or neither in the homework. It might be useful for your project or in the future. Because now these days, right? I mean, with the AI, everyone knows how to do program. If you fall behind, then actually you fall back a lot. And probably you know, right? Although I cover Excel in this class, and Python will be soon added into Excel as well. So I guess if you have time, you can attend the Python optional tutorial. I think 2 weeks later, right? We have a B.A. lab. So if you want to use the computer there, make sure your B.A. lab account is ready. Okay, otherwise you can't open it. Make sure the B.A. lab account already in your email. I think when you join the B school, to check the email, make sure your B.A. account there. Otherwise, you bring your own laptop, will be fine. But just make sure that work is optional. I think it's after the Chongyang Festival, that Tuesday and Wednesday night in the B.A. lab. So you can join either, or you can watch the video. I record that as well, and I'll put a slide later for the Python. So the goal of today is I don't think we can. I mean, we try to finish this, almost finish this. Slides, random variable, not everything, but I'm for sure that we will able to get most of things done. So just to quickly remind you what we are doing, since we talked about this on Monday, where some of you may not be there due to the typhoon, right? And then the bad weather. Just quickly remind you what we are doing for this topic is the application of this is what we call probability modeling. Okay, we are going to give you a framework to understand uncertainty, to measure them, to make judgment, right? Because remember, probability is what we call a measure of the uncertainty, right? Measuring in future, and then how to quantify the uncertainty, right? And random variable is looking at a measurement, right? And measuring what might be the outcome, right? Give a number measurement, and we try to give number how likely they arise, right? Is the random variables doing, and we talk about two different ways to put numbers and measurement of the future, right? One is the discrete, one the continuous, right? The future possible outcome can be a natural number 1, 2, 3, 4, 5, like arrival of customer, right? Then the discrete. But when it continuous, like how long does it take for something to happen, right? That is a time dimension, right? So, or what is the stock price by the end of the day? The stock market index with temperature. These are the thing that's continuous. Okay, so that would be the case. Okay, I'm not going to do a detailed review, but I focus on the main thing, right? And for the discrete random variable, right, which essentially focus on, usually you can imagine, not natural number 1, 2, 3, 4, 5 and 0, right? And to describe that, we use the big P, right? the big P is the thing we describe, right? Because it will tell us each possible number, what's the probability, right? So the foundational thing is I know the P, then I know how to quantify the future. And of course, you can use another one related to big F. The big F is just stacking the P up, but big F and big P are the same thing, right? Just to remind yourself graphically, right? P is telling us each number, what's the probability, and big F is what is the probability less than or equal to that number, but basically just stacking the P, you get the F, and you destack the F, then you get the P, okay? And why we have this? Because when we have continuous random variable, right, that is, sorry, then you will look at the F, right, the big F. And after that, we talk about expectation and variance, right? The big P is sufficient for description of a discrete random variable, okay? But the thing is, the big P can be very complicated, right? And so if we want to have some idea what about the P is, then we have to come up with something. And the idea you do is expectation and variance. The same as idea of data, right? Data is a very complicated thing. And in order to get an idea what's going on, we have a mean, right? And to see how good is the mean is the variance, right? The same idea here, right? The idea is like, suppose you do this hypothetical experiment in your mind, right? And many, many times, and average of the value, right, is same as expectation, right? So basically is, if I want to describe a random variable, a discrete one, I have a big P, but this guy can be very complicated. So in order to understand this, I look at the expectation and the variance, right? And that's actually what we do the finance, right? Finance usually we care about the expected return and the risk-return trade-off, right? When we talk about return, it's about expected return. Risk is variance, okay? So that is the two number that usually we care, right? But of course, you would care the whole P, right? And some of you would wonder, hey, why we learn topic 1, we learn skewness, we learn kurtosis, why I'm talking about here? Yes, they are, but the thing is we are introductory class, right? So if I taught those, that would be too complicated. But you can talk about kurtosis, skewness in this context as well, right? But we are being pretty simple here, just not to talk about those. But and also worry about covariance, right? We talk about two random variable. In topic 1, we also have that here, but we don't really go into detail. But you can clearly see that you can talk about covariance here, right? And for discrete one, let me quickly review what we are doing, because that is the main thing, one of the main things to learn from this class, right? At least the first half of the semester, we learned the probability modeling, right? And probably you will recall when I was student 20 years ago, like you, studying this class, it has 2 classes, okay? Two semester course. After 1 semester, this is what I learned. Okay, this at the end of the first semester, I learned this, and that's the end. Why? Because this by itself is very important, because you learn how to model the future, right? If discrete, you have the big P, right? But the big P usually will unstructured, right? It can be any number, can be any probability. So how do we study? Usually it's come up with many kind of classical thing. It's called a binomial, Poisson, and hypergeometric. There are many more, but these 3 are the mainly binomial, Poisson, hypergeometric is a very useful one. And of course, look at Wikipedia or other stat textbook. There are many kind of distribution you can use. Okay, but these are the useful thing for our introductory class. But that means that if you in the future you face a new distribution, you can just look at what the mean and variance, how they use. It shouldn't be an issue, because you learn 3 of them. And some of you will be say, oh, this is so complicated, I don't go full detail. But we are not stat class, so I can go to every single detail for this distribution, but not you are in the university, right? So I teach you the basics, then if you want to go further, you can do it by yourself, right? I can't. It's like we only have 30. I mean, I think we have like 4 hours. for 13 weeks, right? With like, yeah, 50 something hours for the semester, right? So, I mean, there's a we can't cover everything, right? But that is what we want to say. So basically just give you an idea what they are, right? The uniform is the most simple one, right? And you would assume everything the same. And probably you ask why we do that. It's the case when you don't know what's going on, it's uniform. And of course, you don't stop at uniform, right? And that's the use of data, right? That's why you learn base rule. Start from uniform, base rule update, and keep update, and then you learn, right? That's most likely that is all the learning method. You have a artificial intelligence, you have the AI. This is how they start, right? You start with everything, right? That's if you remember how the AlphaGo, right? They train, right? It's like they have two AlphaGo compete each other. They learn. That's how they start. Start from uniform. Let's start the frame that is the most unbiased. I mean, prior, and then go on. And then your binomial and Bernoulli, I think that is so closely related, right? Bernoulli is the most simplest thing is you would consider the sample space. It just consider as either success or failure, right? There are many outcomes possible, but you just consider one of them, partition them, right? Cut them into, separate them into. These are successful, these are failure, right? The success of the P. And then this is the thing that we often use, right? And you do survey, right? You ask people whether you like this product or not, yes or no, right? Whether you buy this product, yes or no, right? This is, or which gender you are, male or female, right? So usually binary thing, right? So that is the idea goes on here, right? Either you're male or you're not male, right? If you consider more than binary, right? Then you can still do a binary thing, right? You're male or not male, female or not female, right? So it's still possible even if the outcome have more than two, you can just still have one category or not that category. Okay, that's still fine. And you have the mean and variance, right? Do remember that the P is the most important thing, right? Because it has a full description of what we're doing, and mean and variance a summary for that, right? And for the calculation wise, we use the big P. All right. And binomial is just simply repeating the Bernoulli trial, right? So imagine it's like you're going to open an N box, okay? Each box identical. The box is a random box, right? The box can have only two outcomes, success or failure. Success probability P, failure is 1 minus P, okay? You open all the N boxes, and then you care how many total number of success you have. You don't care about the order, okay? This is binomial. If you think that this is what you expect to describe your future uncertainty, you care, use binomial, right? So remember that is how we use it to model, say, how many customers like the spicy food, right? And then you would see how you do the inventory management, right? This problem. Or you can see how you are trying to model, allocate your production resources, right? And this is the slides, right? And then this is the formula here, right? Oh, sorry, there shouldn't be a question mark here, but this is the P, okay? And the next will be Poisson, right? Poisson, the same idea of binomial, right? Binomial is open-end boxes, right? Each box have P. But instead of N, you have many, N is very large, many boxes. Okay? The idea is in consider the time horizon, okay? Each small time interval is considered a box, okay? And you open box as time progress. And if box open, it means something happened, right? And it has been shown when N is large, okay, and P is not very big, then you end up here, right? This is the Poisson, and that is the remember, right? Lambda is NP and E is it's the electron number. Okay, it's 2.718, and the P, actually remember, this P function is describing everything there, right? It's everything that you know, and you want to summarize, then you will be the mean and variance. Okay. And lastly, we have hypergeometric, right? Remember, graphically, what we do is we have big N object. All of that, A of them are good or successful, we consider, and N minus A consider bad. Okay. And we take N item out, okay, without replacement. Okay. If we take thing out and put it back, then it becomes binomial, right? Because that is what it means, right? Because the success will be A over N, right? But now it's just we put it, take it out and don't put it back. Okay. In that case, we're asking out of N small N item we take it out, how many of them are good? Okay. And the reason why I use this NA whatever X is because of Excel the notation. So I just try to follow that notation. So although it doesn't not very nice, but this is what it is. Okay. So this is the hypergeometric one. Okay. And this is the probability function. And this is the mean and variance. Okay. And do remember what's the application of those is quality control and audit, right? Because that's what you do, right? Go to the warehouse and the client tell you how many A, how many N minus A, right? And then it's your choice to pick up the N. You can decide how large the N is, and then you calculate the X, right? And with this probability P, right? And you can make decision, right? You can decide how large N is and what is X realized, then you would consider that the evidence is supportive or not supportive. And to go beyond, of course, you have to look at the your auditing class, but that is what it is. Okay, because this is a complete description of this process, right? And you can based on this to make decision. Okay, but you can see what we're doing is trying to tell you how to calculate future probability, right? And based on some assumption, right? This is called probability modeling. And that is a very important thing because there's a language you study the future, right? I mean, business involves future planning, right? And that's why everyone in B school, regardless of the statistics, you have to study this, right? Because without this, how can you quantify what you mean by future, right? I mean, that is have to come up with some educated explanation, not just a wild guess, right? This tell you, even though you're making wild guess or supported by some assumption, and we can discuss whether this assumption is valid or not. That's the reason why you need a math model to behind. It's not because we need math is for technical reason for the method. For having a model, having an assumption, then you know whether the conclusion you get is reasonable, right? Whether you get the right thing, right? So continuous random variable here. And one of the reasons that we, I add some slide, but this already talked about, so there's nothing new here. And the reason why we need to have a new thing is because we cannot have P of X, okay? The reason is because of continuous random variable. It means that there are many number, infinite many, so many that you can't count them. So it means that if any number that has positive probability, you add them up, then it's more than one, right? So there's no way you can use P, okay? But F is still well defined, okay? Because it's asking less than that number had the probability, that's no problem, okay? So that's why when we talk about continuous random variable in our class, we will focus on big F, okay? The big F is the thing we define, just like the discrete is always the big P, and the continuous is always the big F, okay? And to understand the idea, you can remind yourself again, this problem of tossing a coin, right? And it's a fair coin. So it's equal likely that you have head or tail, right? So it's 1 and 0 is like this, right? And suppose you have instead of coin, you have a die, okay, a three-phase die, okay. Three outcome is equal likely, right? And the P will be just again a flat one, right? Have a phi bar at 0, 1, and 2, and this F is stacking up, right? And you can easily see that if I increase the number of outcome, okay, it's still a flat one, right? And then it's increasing a line, right? Slope. But the problem goes when I have infinite many outcome, right? Because look at this. This is 1 over n, right? Each outcome is equal likely, and the height of the bar 1 over n, the 1 over n will go to 0, right? Because there are many outcomes. 1 over n just becomes 0. So this px is not relevant, right? Because there are so many outcomes. So how can you assign probability, right? So that is the idea that we can't use the p, but rather we use the f. Okay, f is px less than x, and some property probably you would not be surprised to see, right? This, okay, be same as this guy, okay. The reason why is addition rule, right? Less than a plus the b, okay, would be the case, okay. And probably if you are very strict, I should use the less than or equal to, okay. I should use that one if you are pretty very strict. If you are, because this is what the addition rule said, right? Let me write that down because some of you probably not aware what I'm writing, right? So this is probability x less than p, right? And this is what probability x or less than equal to a, right? You move the other side, right? Less than equal to a. Oh, sorry. And I should not have this guy, sorry. Right? Less than equal to a plus a to b be less than b, right? So, but whether you have this underline or not doesn't really matter because we have continuous. Here we mean truly continuous. So which means that there are no Porter probability. So that's why the same thing. And the complement rule will tell you more than b will be just 1 minus b. So that will be rule we are using. You notice that very soon when we work out. This I just put it there in case. So I think this is a relatively new slide. I just add them in is because I don't want to use a limit to define it, so I just define them loosely. What is the small f? Small f is the following. Okay, so you're the random variable and two number b bigger than a. Okay, the probability that within this interval, okay, will be the length of interval times the f. Okay, so what does that mean? I mean, let me put it there. Actually, this is no different from is what is said is like this, right? It's x, it's f, okay, and I have a and b, that's f, okay. This length is b minus a, right? I pick a point here, okay. This is the height, okay, and I would say this, the f, this area is the probability, right? If you learn integration, this is very natural, but the same as the bar chart idea, right? So this is the bar chart here, right? So just tell me if this is small enough, this is the probability that the number between a and b. Okay, so that is the roughly idea of the density function there. The small f means this. So that if this is small enough, you just this rectangle represent the probability. Okay, that is what exactly it means here. Okay, and if you rewrite this, right, you say the density because you say from x to pick a number divided by this is the f. Okay. Of course, you can multiply delta this side, right? So the same as this one, right? So that is the idea of density, right? It's just like the standard idea of physics, the density idea. Okay. And I'm not talking about the calculus idea. Okay. But this is the graph that you should remember. We were using it all the time, right? I have f here, I have a here. All the area on the left-hand side is called f of a. Okay. If I have a here, the right-hand side f1 minus fa. And if area between a and b, if fb minus fa. So this is the graph that you will be using for the rest of our course. So this is something that, don't worry, you must know. It's hard to miss it because we'll be keep using this for the rest of the semester. Okay. We'll be using this guy. So that's, I mean, although I put it here because I think it's useful, but this graph actually appear later in today's slides as well. Expectation and variance. The continuous has the same idea, right? Expectation actually still mean if I repeat doing this many times, what's average value, right? And variance is the same idea, right? How each value different from its mean. Okay. Although by integration look crazy, but there's no difference from that. If you want to care, this is how you take it from here from integration. If you know integration, that is actually what it means. But in our class, we didn't require any integration, so that should be fine. So we just still understand conceptually, mean is the same as mean, variance and mean. Okay. There's no particular new thing here. So I guess I have time today. We'll go over from uniform to normal. If I have time, we'll go to chi-square, student T and F. But this 3 is the thing we learn for this class. And actually, for the rest of the semester, we will work on this 3. So I just very briefly on this 3 only, tell you what they are without going into detail. This 3 will be probably we don't cover chi-square in our class because of the time constraint, but we'll cover these 2 in detail. Okay, so later you will see. So uniform, this is the way that how you learn small f and big F. And the easiest thing you can imagine is uniform means that there are 2 numbers, a and b, and any value between a and b is equally likely. Okay, and the way that you will see later, I explain, f will be 0 outside the region, and within the region will be constant. Okay, and I'll explain why the constant is this one. Okay, and let me explain now why is this guy. Look at this graph here, f. Outside is 0, I think there's no concern because the number is between a and b, so outside is 0, there's no problem. Y is flat and y is constant. Flat, I don't think is an issue because uniform, so which means that the same, right? Because you remember the discrete version, the height of each outcome is the same height, so this will be the same, right? So the idea why this is 1 over b minus a is the following. You have to remember that the area under the f is the probability. So let me repeat the statement. We learned what is a small f in the continuous random variable is area under f is probability. Let me repeat once again. It's very important. Area under small f is probability. Good. Now, because we are talking about probability, we know what's going on. The number you have happened here must be between a and b, right? So it means that the probability must be 1 between a and b, right? So since area is probability, so this means that this area must be 1. Okay, and area is 1. This is a rectangle. Rectangle under primary school, you learn rectangle is what? Base times height, right? So what's the base here? Base is b minus a. right? And the height must be what? B minus A times what is 1? It's 1 over B minus A. This time this is just 1, right? So that's how you get the height. Is that clear? Right? Suppose this is 2. This is 1, this is 2. Then this must be 1, right? So that is the why you get this one. So I hope this convinces you why this is one you know. Okay. And this is the only time we will study the F in math. Otherwise, we will do everything F in conceptual. Okay. This is only the quantitative study work for F. Okay. And otherwise, we will just look at the shape and that's it. Not going into detail of how it looks like. Okay. The next is big F. Big F is what? Big F is probability that x less than or equal to x, right? It's the probability less than or equal to that number. Okay. What does that mean here? Suppose I put a particular x. Okay. Maybe other color. Red is not good. X here. What should be the height? Right? Height is the probability that x less than or equal to this particular number x. Right? So what does that mean? It actually means the following. X less than or equal to, right? So this whole area. This whole area should be same as this number. Okay? And this area, how to calculate the area of a rectangle? Remember, is base times height. What's the height? B 1 over B minus A. What is the base? X minus A. So that's why you see in the slide, this line is given by X minus A over B minus A. Okay? And why is a line? It's easy to see. When X is A, this guy is 0. Right? Before that is 0 as well, right? Because there's nothing before, right? The area before the 0. And when X is B, this is 1. Right? From there on it's 1. So, and this is linear in X, right? Like this, right? Because it's linear. Is that clear? Okay. This is the only time we work the math. Okay. After that, we're not going to work on this graph mathematically, just graphically. So this is the only time you will have F and big F. No more math on this one. So just conceptual from that on. Okay. Because this one you can calculate because you don't know calculus, so we can't do anymore. The reason is not that it's not important because you don't learn calculus, so nothing you can do. Okay. So this is the time we do the math here. Is that okay? Good. So now here is the, remember we have the big F when you have this, we have the continuous random variable, F is the thing we care. And this is the full description of the random variable we care. All right. And then we can come up with the summary statistics like mean and variance. Okay. And mean is very simple, just the middle value, right? A plus B over 2. And variance will be the square of the range over 12, like B minus A is a range. And don't ask me how we get these two, just calculus. Okay, just calculation, and we don't really care because what we use is use this number, right? You ask people, tell you, okay, I think the future, right, is between this and this, and this often happens when you look at the TV shows, the financial news. You ask the expert, so-called expert, they will say, okay, what is the Hang Seng Index today? Okay, it's going to be 15,000 to 16,000. Okay, then he didn't mention about any distribution. Then the natural thing you would conjecture what his mean is actually meaning uniform, right? It's a uniform. Actually, it's a uniform between 15,000 to 16,000, and then you actually can calculate the mean and variance, right? That's how you do the calculation, right? So that I hope that would explain the thing, right? And as I said, if you can do the example, you have the mean, right, and the variance, right? Here, A is 1, B is 4, right? Because between 1 and 4. Is that clear for this one? Okay, you will be doing exercise for your assignment for this kind of thing. So if you understand the green thing, then it should be fine. Of course, you're good to understand the purple thing as well. If you're QFN, I expect you to also know the gray area. Not for this class, but if you want to go further, okay? I think the 2000 class still is fine. But when you go to 3000 or 4000 classes, knowing the gray thing would be important. Okay? But anyway, shouldn't be a matter. When you need it, you can pick it up, right? Because the thing go to college is you know how to pick up stuff, right? I hope I teach this, you know how to pick it up. Okay, I touch the basics. So here is a uniform from 1 to 3, so 1 to 4, and more is between 1 to 3. Okay, and technically this actually means this guy, right? I think I give you the thing, right? Just you plug in the number there, then you're done, right? So there's nothing new here, right? Just plug in. I think it's easy to see why this is true, right? Because 1 to 3 is less than 3 minus less than 1, right? Because that is between 1 to 3, right? So just plug in the number. I don't think this will be easy. Say it's between 2 to 3, then the same idea, right? Just F3 minus S2. Is that okay? Now I want to talk about this exponential. The reason for this is one of the most useful thing, right? Because Poisson is very useful, right? To measure how many people arrive in a certain period of time, right? This is modeling customer comes in. And this one is exactly following the Poisson idea, okay? Poisson is saying the following, right? If you still remember, let me draw a graph. So Poisson is the following, right? Poisson is asking, okay, I have a timeline here, say for 0 to 1 hour, right? You can cut this into 60 minutes, 60, and then you can cut each minute into 60 seconds, right? So and so forth. Cut it very small, right? You have a lambda, right? Lambda is on average how many people arrive in an hour, right? That's how you do Poisson, right? And then we have no problem modeling this kind of problem, right? How many people arrive, how many accidents will happen, so on and so forth, right? And the question we might have is, okay, how long does it take for a guy to come in, for even to happen, right? Poisson is asking how many will be there, okay? And exponential will be asking how long does it take. For example, how many of them arrive? This is Poisson, okay? But if you're asking how long does it take, it's called T1, and this is T2, T3, right? All the time. This time also random variable, right? It depends on when they come. And this time will be follow the exponential distribution, okay? Let me repeat what's the exponential. Assume the arrival of the event or people or customer, right? Follow a Poisson distribution, right? And we understand what's Poisson, right? Because you assume it's a binomial, right? It's like every period is independent, right? And if you think that arrival is independent over time, okay, then it's a Poisson. Then the time for things to arrive is exponential. And exponential, we don't prove it, okay? And we can show the big F. Where's the pen? The big F follow this guy, and small f will be this guy, okay? And we don't prove it, but you can actually prove it from the Poisson, okay? The Poisson you can do calculation. It's way beyond the scope of our class. If you want to really understand it, you go to the stat department. They will teach you how to do that. I have some intuitive proof in the slide, and if you want to look at them, they're there. But the actual proof require way beyond the technique we learned in our class. But what we need to learn is this guy, the big F, right? Because remember, in our class, you need to do big F, right? Although I have integration, they're showing you how to prove it, but this is the thing. And why we care about the big F and small f? Because the name exponential comes in. Look at this one. This is typical exponential graph. It's like you just dropping, going down. And for those who actually learn atomic physics, that is what the radioactive decay goes on. There's a radioactive element there. The time it takes to emit some atoms is like this one. But doesn't really matter. We are not nuclear physics class. So, but this is how you think of exponential, right? Is very likely the probability is very high at the beginning, but it's keep decreasing. Okay. It's not uniform, right? It's like and this is the thing you need to know, right? Will be this big F, okay? And probably it's good to understand the mean of course the variance is a little bit more complicated. First, do note that the variance and mean are different. Different from Poisson, right? Poisson, mean and variance are lambda, right? But here, the mean and variance are different. Mean is 1 over lambda, variance 1 over lambda square. Okay. Let me give you an intuitive explanation why this is 1 over lambda. Okay. So 1 hour thing, lambda is 2. Okay. Suppose a Poisson with lambda 2 means on average there are 2 people come in my store, or the 2 event comes out, right? On average 2 events. What does that mean? You mean on average you expect what? 2 outcomes, 2 people come in, right? So that means that you expect somewhere in the middle, somewhere at the end. This is what we mean by 2, right? And what does that mean? It means that how long does it take for one guy to come? Half an hour, right? So the time for this to happen is half an hour, right? Or 30 minutes. Okay. So that's why the mean is 1 over lambda. Is that clear? Of course, the variance is a little bit more complicated, but we're not going into detail. If you want to prove, you got calculus and integration by part, which is advanced technique for calculus. So that's why we're not going to go for that. But you know the mean and variance are different. Okay. So let's see the example and then we'll break. Okay. So just remind yourself what is the purpose of doing exponential. Exponential is modeling what? Time for things to arrive. Okay. And this is the basic modeling tools that you use. And the only restriction you can see, or the main restriction you can see for exponential is saying that throughout the period, it's the same. So because it's actually borrowing from the binomial, right? Binomial saying you open a box, each box is the same, right? The probability of success is the same, the arrival rate is the same. So that's why when you apply the practice, okay, suppose you want to model, same as Poisson, you want to model, say, the arrival time for a customer to come into a restaurant, okay? If your restaurant is supermarket, that might be okay. Over the day, maybe similar. But if your shop is a restaurant, then it can be issue because restaurant people come in more time, more customer come in the lunchtime, come in the tea time, come in the dinner time, right? And the time between meals is much less, right? So if you really want to actually apply it in practice, which we will learn in the advanced classes, you will separate each time period different, right? Dinner will follow different mean, lunch will different mean, but there's no problem as long as you segregate them. Poisson, the exponential of Poisson will be a good approximation to what we're doing. Okay, so here's an example of saying that the customer arrives with exponential mean of 20 minutes. Okay, and what's probably the next one arrive in 10. Okay, and the thing that you need to notice is mean is 20. Okay, and do note that mean is 1 over lambda. Okay, look at the slide. Mean is 1 over lambda. So you have to look at equate 20 to 1 over lambda, which means lambda is 1 over 20. Okay, and then you just plug in the question required. The question asks you within next 10 minutes, so it's less than 10. Okay? So that is how you're getting the answer just by plugging the f, right? Because the f is what? F is 1 minus e negative lambda x, right? And lambda is 1 over 20, and x is just 10, right? So do remind yourself, for exponential, I just need to know lambda, and that's it. As long as I know the lambda, or I know the mean of the people arriving, then I'm done. So this is very simple way to do things, right? Because I only have data, look at my shop, how many people arrive, how long does it take for one customer arrive, and I can easily do the estimation. Is that clear? I hope that would be a easy one. Okay. And let me look at the other example with a break. We'll have a break very soon. After this example, we'll break. Okay. Sorry, a little bit longer, but I think it's good to have a complete example. So another example is actually very similar. The same process, but instead of asking less than 10 minutes, I ask 5 to 15. Probably ask what's the use case of this. Maybe your staff want to go to washroom for 10 minutes. Okay, then calculate the probability, you can know what to do, right? Or maybe you need to send the staff to somewhere else to do for 10 minutes job somewhere else, right? So the current probability, right, between 5 to 15. So just to remind you that whether inclusive 5 or not inclusive doesn't really matter. Then right here, I'm being loose, but for our use case, there's no difference. So whether you have no inequality or not doesn't really matter. It's still 15 minus 5. Okay, and just plug in the number, then you're done. Okay, and now you may worry about how to plug in this number. Next week, next Monday we don't have class, but next Thursday, we will probably have time to tell you this one in Excel directly calculation. Okay, you don't even need to worry about this. Excel will tell you this number, then you're done. Okay, so it's not that complicated. You plug in the Excel, just put in the function, then you're done. Okay, and you can do all the calculation easily because that is how you make decision, right? In the future, you know the time for things to arrive, then you can make decision, right? And also you can see, do I have example? You can look at the example in the break. I think that is something obvious. You can do that. There's no problem. So that's a break for 10 minutes. In the meantime, I put down the slide. Then you can tell me what are the things that you want to know more. So now it's let's assume the time. Appreciate that you fill in the form as a way of attendance and also elicit your questions. I go around to see if any question. So I guess I should resume to see how you feel about the class. Okay, let's check it out and see how the speed better. Okay, that's good. I guess if the speed is similar, but the thing is like you're used to that because as you can see, the similar thing discrete and continuous, and it should be something very comfortable from now on because I think this was I think the most difficult one because conceptually you learn a new language of probability, and from that on actually we are applying everything from now on should be okay. Most of you I say okay. Hopefully it's not that difficult. Okay, today is good. Everyone knows it's Thursday, and okay, so it's cloudy and windy. So this is always we never have consensus, even the weather. So you can see the statistics are always you never have 100% of, regardless of what. I guess it's good news today. We have more people getting 4. Okay, I think most of the time, I mean, I always get people think I'm very slow. Okay, that's always like this case, but I don't know whether slow or fast, but maybe I should have the fast or slow. Because appropriate is not really. Maybe I should change the next time. It's fast or slow because I don't know whether fast or slow. This one good. Okay, I think it's like still a little bit too fast. But some of you actually think I'm too slow. So, but I guess if the speed is okay, you can see this is a bimodal distribution, right? Usually you have a bell, but today we have like two peak here, right? You have 2 mole, 10, right? And in fact, this is usually the ideal case because for teaching, you should be expecting cadence the median. Half of the class would think I'm too fast. Half of the class I think I'm too slow. I think it's a good one, but I try to make sure that you would be okay. Yeah, we have only one joke today, which is ha ha ha. But so I hope you would be seeing how you use exponential. Okay, let's just we'll quickly go over that again. So exponential would be like you can model the surface time for you, I mean, to see how long you wait, right? That's you see in a lot of the chatbot or the online app or the telephone you call, you just say the next customer service available to you is like 10 minutes. How to do that is exponential, right? And you calculate how long does it take for equipment to fail, right? That's very normal. Actually, the operation people would care. Inventory management, we have talked about that already, right? And for example, in the case we don't discuss, but also the restaurant that cook the spicy food, right? Then you need to mention how long does it take for you to replenish your stock, right? You can apply to that. Also project management, you can see how long does it take for bug to come in, how do they solve it. So a lot of application, right? Because you're modeling time, so exponential is very convenient. I think it also related to ideas, what somewhat related to if the accounting look like the depreciation. Although I don't learn accounting, but I still remember somewhat like you have a straight line depreciation, right? And you have like double accelerated. I don't know, is it like that one? Double accelerated depreciation like exponential style. Okay, but that is the case, then it's like if you have a straight line, then it's like uniform, right? And then if you believe the depreciation is like exponential, then it's like the double acceleration. I forgot. I mean, you guys can tell me because you guys are expert on accounting. I'm not, right? So you probably know more than I do. But that is there's a rationale behind the accounting rule you use, right? Because you can justify the depreciation rule by thinking the time to fail if uniform. There's a straight line. Right? But anyway, let's don't worry about this. Okay. Now we come to, I guess, the most important of our course, basically the cream of this class or the course as a whole, the bell curve. Okay, let me introduce you the most important thing, bell curve, and probably you have learned it before. Okay, and bell curve mathematically is the most complicated object we ever describe in the class. Okay, but don't worry, we never use it. We use computer, but so let's start with bell curve. Bell curve by definition is a bell. Okay, so let's see the bell first before we go anything further. So these are the bells. So the blue bell, green bell, and red bell. The bell is like this and symmetric. Okay, and I think we mentioned bell in when we mentioned kurtosis. Okay, but bell, one thing first is the support is go to negative. Okay, and you do notice that when we learn about the exponential far from 0 to infinity, here is from negative infinity to positive. So there's that means any number is good. Okay, that is the normal. So that means that there's no restriction on what number you can be there. So that is very flexible. Okay, but of course you may worry about things that cannot be negative, like the price is bounded by 0. So can we apply this to here? Later you will see this is not an issue, because although it's not bell, later you will learn we call the rule of thumb a micro rule. 99% of the time is within 3 SD, 3 standard deviation. So as long as the thing is big enough, you don't need to worry. Okay, unless the range is very big, then you worry about the negative. But to model stop price, you can use normal. That's no problem. Okay, and the second thing is you can transform the variable you care. Right? You think about stop price. Okay, price cannot go negative. Right? But how do you use normal? You don't use stop price per se. You use return, stop return. Return can be negative to positive, no problem, right? So you can not focus on the variable, you care about the transform variable, that will be fine. Rate of change can be negative, no problem. Like, right? So the bell, the shape is very elegant, but the math is not, maybe you can say not so elegant. Okay, look like this guy. Okay, I still put it here because this is so common, we have to know what it looks like. Although we don't need to recognize it, but we have some idea what it looks like. And you can see there's a pi here, there's e here, so you can ensure yourself this complicated enough. Okay, and I hope that two familiar symbols you can see is mu and sigma square, right? Mu and sigma square. And you're right, mu actually is a mean. Sigma square is actually variance. So this is the two numbers that characterize the bell. So for every bell, you really need to know the mu and sigma square. That's it. I'll talk about this more. Okay. And you can imagine a big F, this complicated object will be this complicated thing, this thing. Okay. Unfortunately, even the greatest mathematician cannot come up with closed form. So we have to do this, we have to use calculator. Even you're the best mathematician. So that's why don't worry. Even you are very good at math, even you're genius in math, there's no way to calculate this guy. Okay, you have to use computer. Okay, so that's why you don't need to worry about this. Okay, I just put it here because of you need to look at this shape. It's good to know this kind of stuff, right? When you see square root and pi and e, okay, highly likely mu and sigma, that's something the normal. Okay, but you don't need to worry about that. Now, I want to mention why this is called normal. And historically, this is called Gaussian distribution because this is invented by a famous mathematician Gauss. Okay, and later people figure out that this one is very useful to model so many things in this world. When look at nature, okay, look at your IQ, the distribution of IQ in the society follow normal. Okay, and people call 100 IQ is what? Actually the mean, right? And the weight and the height is also follow normal. Okay, or a lot of health indicator, look at the health report. Everything is also normal, right? When you talk about your BMI is what? Your cholesterol level, many of the things actually called normal, right? And people and the doctor will probably call you overweight or underweight if you're more than 1 or 2 ST. Later we'll see why that's the case, but that is very common. And probably you ask, okay, why we have so many bell curves in the world? We observe the natural data. The reason we'll talk about a little bit in 2 topics later, we talk about what we call is very important theorem in this class is called central limit theorem. We'll talk about the 2 topics later, which essentially said the following: if what you observe is average outcome of many things together, that will come a bell curve. Okay, so what do you mean by that? Look at your IQ. How your IQ being determined? Depend on your DNA, depend on your parents' IQ, depend on your great parents' IQ, depend on where you study, depend on what you study, depend on what food you eat, maybe also depend on the location of the star, right? To people who believe in the cosmology, right? And maybe depend on which year you're born, right? Location of the moon, whatever. There are many things there, right? Same as the weight and the height, right? It's determined by many things, okay? And many is roughly random, right? Then you get the bell curve, okay? And that's the important thing because later you learn the central limit theorem is the underlying concept for all the things we do the second half of the course, because the bell curve is something that we determine most of the stuff we learn. Okay, so that's why, as I said, this is if you forget everything in this class, for sure, bell curve is something in your head because that's the only thing we learn for the rest of this from the second half of the course. Okay, so that's why the bell you never forget. Okay, don't worry. So that's why don't worry about it. You're getting increasing easier because we always work with the bell. Okay, so the bell is like that. Okay, so remember the bell. I said only 2 things to determine: mean and variance. That actually the mu and sigma square. Okay, and mu is determine the bell location. Look at the red one. Mu is 0, so the peak is at 0. Okay, the green one, the peak is also 0, and the blue one, the mu is -4. Just look, it's shifting left and right. The location is the mu, right? And the shape, okay, is the sigma square. Remember, sigma square is the shape, the spread, how spread out, right? Because of variance, right? The spread. And you can see compare the green and the red one, right? And the red one has higher variance when it's 4, the green one's when it's 1, right? And you can notice that If you try to squeeze the red, you become green. Okay. Why is squeezing? Because this is f, right? Small f. The area under the curve must be 1 always, right? So that's why in order to from this high wave low wave, just squeeze them up. Just squeeze it, right? Is that okay? So that's the shape. Okay. And as we have said, the mean is mu, variance is sigma square. Okay, that's how you understand the normal. Okay. Now, one extra thing you probably would know, probably is not something difficult, is this is symmetric, the bell, left and right the same. Okay, symmetric bell. That's why skewness is always 0. The other one is kurtosis is 3. That is the definition. Okay, so if have more fatter tail than bell, then it's called the fat. Is thinner than bell, then it's called thin. Okay, that is the definition. Bell is the relevant thing. Okay, so we have some notation here because bell is so common. Okay, a normal is so common. We have a notation. Okay, we will call x. Okay, if it's a normal distribution with mean mu sigma square, we'll write the shorthand notation. This is the standard notation in all this textbook. So it's not invented by me. Every textbook you read is like this. Okay, we'll call x. This snake is distributed as, or you can say follow distribution. Okay, follow distribution of n is normal, and with mean mu and sigma square. Okay, so this notation is you can find every stat textbook. Okay, so just put it here because that will make our life easier. Okay, and also you understand what's going on when you read other books. Right? Now, the first thing I want to say, okay, is the bell has very many nice properties. Okay, and turn out that this is very convenient for us to do a lot of stuff. Okay, first, if I have x and normal with mean mu and sigma square, what do we have when we have ax of b? Okay, and this turnout is not complicated. Okay, remember, expected ax plus b is what? A expected x plus b, right? If you still recall this formula, right? So this is mu, so you get this guy, right? Variance, the same idea, right? If you still recall, variance ax plus b is a square variance of x. So if these are known, what's new here? The new here is saying the following. When the bell is the thing, ax plus b is also a bell. So this is something that is not true for general. Okay, if you have a binomial, your times a plus b is not binomial, right? Because binomial must be from 0 to n, right? Your plus b is no longer binomial anymore. Okay, so this idea of you add and multiply and add thing, it remains the same, is unusual. Okay, and why is it good? Why is it useful? Because suppose you try to model IQ or you model other things, okay? And that explains why when you do some aptitude tests, you do the IQ or you try to do exams, public exam, you find also you see a normal, right? Because you could imagine that is no matter what kind of marks you are doing, it's a normal, right? Regardless of the exam is 100 points, 30 points, whatever. Okay, normal is the normal. Add things to normal. Remember, x, suppose you're modeling the share price. Okay, if the share price follow normal, if I look at my portfolio, which I have a share of x and b amount of cash, my portfolio will also follow normal. So that is unusual. Okay, it's not necessarily true for every other thing. Suppose a is exponent, x is exponential. I do that, it's no longer exponential. right? Because exponential start from 0. You add b is no longer exponential. Okay, so that is a very special thing. Okay, it's not generally true, but because this is true, make our life easier. You will see immediately why this is true. Why is it useful? Because of the following. Can I move to the next slide? Move to the slide. The reason why this is important because of what we call standardization, Z score or the Z. Okay. The reason is for normal, you have many different mu, different sigma square, right? Then there are many bell curves you can imagine, right? Because different mu and different sigma square, different bell curve. But do we need to worry about that? No, for normal. Because if we set A is 1 over sigma and B is mu over sigma, we can always transform it to normal C1. Okay? And why is important? Why is important? Because recall, we can't wait to calculate this guy. If every time is different, this guy is very busy, right? And that's why if we always can transform things to this one, our life is very easy, right? Because we only need to look at one, okay? If you look at X, I always do the transformation called Z, and we're done. Okay? So that's why some of you learn in high school, they call the standardized score. This is what it means. Okay? This is standardized score. And standardized score only apply when it's normal, right? It's not normal. Standardized score has no meaning. Well, of course, in high school is still considered standardized score, but it's not meaningful unless it's normal. All right? Right? Actually, look at your GPA or look at your grade, it's actually standardized, right? You compare different class, right? You don't call about marks, don't give your marks, right? You A, B, C, D, right? But some mean A from a 1,000 class, 2,000 class, 3,000 class can be mean very differently, but you still normalize, right? It's compared to the average of the class, right? That's how you get things. So anyway, standardized normal. So, and as we said, with this calculator, right? And how do we do it in our class, right? And especially for the final exam where you don't have computer, okay? What we do is what we call the Z table is the classical way to do it. And of course, this thing in Excel already. So the Excel table gives you the FZ, okay? And we only need the standardized normal because the property, right? No matter what normal, we can always look at the standardized normal we find. So there'll be two versions. One is less than 0, one is bigger than 0. Okay, because it's symmetric, but the same thing. Okay. So let me show you what you might get. Okay. Look at this example. Okay. I want to look at the probability Z is less than 1.4. Okay. So that is the question. Okay. And just what does that mean is like this. Z of a bell. We have 0 here. Okay. And what we want is 1.4 in this area. Okay. This is what this question means. Okay. On the left of 1.4, what's the area? Okay. And of course, there's no way you can calculate except you do Excel. Another way is to look at the table. Okay. I'm going to show you the table. You can Google set table. Okay. Easy. But I think this is the area they asked. Okay. I actually put it here. Okay. This is the typical table. I mean, if you don't like this one, I just go to I can just Google it. It's fine. Set table. I use dummy. It's easy. So use set table and dummy. And lower set table. This is the style we get. So this is the table we have. Okay. The normal, there's called a set table, Z table, or so the one we need is this guy, less than 1.4, So I net Z less than 1.4. So to read that is look at this and go down to 1.4. So it's this number here. I don't know whether you can see that clearly. That's why I, in the updated slide on the web, I just copy here. That's it. This is negative version. The table is negative. I go to the other one. That's positive. So it's this guy. So how do you read this one? This is f of z. So you would first read the row first. Okay, it's 1.4, and this is 1.40. This 1.4, 1.4. Is that clear? I will do more example. Don't worry. But this is how you read this number. This is DS entry. It's z 1.40. Okay. So I will do several more. So don't worry about that. Okay. This table is same as the table I look at any table you look at the web the same. So this is the same. Okay. So let me do another example. Don't worry. We will do more until you get it. Okay. So this is less than negative 1.6. Okay. So you can look at this one. Okay. This table, negative 1.6. Let's go down, right? 1.6. So will be this number. 1.6 is here. Okay. Is that clear? Or you can go to my slide, which is essentially the same thing. Okay. This is the stat table. Right? Read the row. 1.6 is here. This guy. Okay. Is that clear? Don't worry, we'll be doing this all the time. Again, and again until we're tired. So because this is the thing we have to use for the rest of the class. So you must be tired of it sometime. So this one is between this and that. So there's subtraction, right? Because it's less than 1.4 minus less than negative 1.4. So we subtract this from this guy. Like that. Is that clear? So if you know the first two bullet points, the last one will be easy. Right? Because that's what it means. Right? Between A and B will be FB minus FA. So this is the shape. So we have what we call the rule of thumb. Okay. You can check it. Turn out to be Z within negative 1 and 1 is 70%. Between 2 and 2 is 95. 3 and 3 is 99. Okay. So does that mean? It means that 70% is within 1 SD, 1 standard deviation. We will be 95% between 2 SD, and 99% almost all between 3 SD. Okay. So it's very important because most of the thing you think is natural, they occur is follow normal distribution, right? So as long as everything within 2 SD usually is within the normal range. If outside 2 SD, you'll be worried about that, right? Even this rule actually apply to not so normal, but I mean, if not normal, then it might be much larger. There are rule, but in general, the thing is normal, so you can apply this rule. So basically, what you are thinking is looking at some data for your accounting, right? Look at the thing, look at historical mean and variance, right? You can look at the data you got. Is it within 2 SD or 3 SD? If beyond, then you would just, okay, there's maybe some problem with the thing is something unusual happening, right? So that's what rule of thumb is doing, right? Because you don't want to worry about, you think about things are normal, right? Within 2 SD or 3 SD, like even usually 2 SD, right? Within 2 SD is not a big thing. Okay? It's natural to have with things within 2 SD, right? Beyond 3 SD, then 2 SD, then you have to worry about that. Right? Is that clear? So that is there's a rule of thumb we use because that is how you make this decision, right? So this is what the graph represent, right? Within one SD, 68. And you can look at the table and check it out. This is true. Okay. And next, we have inverse normal. Okay. And what is here? I'll talk about this because we will do this when we have application, and this is Excel function we learn. Okay. So what is this guy? So don't worry, this is super simple. I draw a graph and you understand. It's something very simple. So far what we said is the table, the set table tells the following. You give me a particular value set, say 1.4 or whatever. The table gives you this number, right? This number is probability, right? The table, the Z table is the following, right? You give me the number below, the table gives you the area under the F, the curve, right? The probability. Inverse is opposite. You give me the area, I give you the value below. So let me repeat the statement. Inverse is you give me the blue area, I give you this number. It's reverse. Go from this one. It's called the inverse. Okay. So let's see the example. There's no new table, but just the way you read it. Okay. So this example is like this. What is the probability that Z less than Z is 0.95? Okay. So basically just go to the table and look at 0.95. Because this table, okay? Although it's huge, but look at the number that closest 0.95. So look at your eyes may be not easy, but somewhere here. I just circle it. This table is a little bit tricky. Maybe I just use another color. Hopefully it's clear. Hopefully it's clear why it is here, right? Here between 0.95, right? So that's why you can put 1.64 or 1.65. Usually you may take somewhere in the middle. Usually they will say 1.645, but any number in between will be fine, right? So, and the other case would be, the question here is like, what is this for more than that 0.025, right? So it only means the following, right? Just draw a graph. It's saying that 0 is here, this area more than, right? So the area on the right-hand side and the right-hand side is 0.025, right? It's the question, but you know the area bottom must be total 1, right? When you say the right-hand side is 0.025, it simply means one thing, right? You mean the area on the left-hand side is 0.975. Okay. Then what we're going to do, look at the table again, right? What is 0.975? 0.975 exactly here. This is 1.96. Is that clear how you read that thing? Look at the row and then look at it, but just reversely. Okay. Where's the mouse? Yes. Don't worry. This is the thing that, although for those of you who first seen this, can be a lot of procedure, but this procedure we will repeat, unfortunately, boringly for the rest of our course. So there's no way you can miss it, but because I said normal is so common, so that's why we use for the rest of our class. either this table or that table or whatever, but they will be, the procedure is similar. So one thing is we'll do is to see, we know the Z, right? So how extend our knowledge to usual normal. Okay, let me draw a graph diagram, then you will see looks like. Okay, so this question I have normal 20 and 16, and I less than 16. So the question like that. Let me draw a diagram. Let me finish this. This is the last example we cover today. So then you have a nice holiday. Hopefully, X is this one. Okay, and the mean is 20. So the bell have located in 20, right? And we have sigma square is 16. So that means that sigma is 4. Okay. So the question being asked is 16 here. 16 here. What is this area? Right? We want this guy. This is the question. How do we approach this? Is remember, we can always transform this to the other diagram. The answer is the same. I transform it to Z. I'll again draw it here, but 0 become 20 becomes 0. Okay. How do you transform this? Is X minus mu over sigma. Okay. 20 minus 20 over 4 is 20. 16 become what? -1. Why? Because 16 minus 20 over 4. Right? -1. So the blue area is this guy. So what we need is look at the area below -1. Right? Then we're done. Let's look at the table. Is that clear? Okay. And I'll just look at the table again, because that would be the thing we need. So don't worry, we'll talk about this again in the next class, but -1 with this guy. 0.01379. Okay, then we're done. That's how you get the answer there. Okay. So I will see you next Thursday, because next Monday the class moved to the end of semester to cover our programming. Okay, so we will see you on next Thursday.